Now that we've gone through our review in trigonometry and algebra, we can kind of get started with the idea of some calculus. Keep in mind that your success in calculus often translates to your skills in algebra and trigonometry, especially algebra. Calculus is divided into two branches, and we'll be looking at both of these branches while we're working in Calc 1. The first branch is going to be differential calculus, and that's what we'll start the class with. Now, differential calculus involves quite a few different ideas, but basically the whole idea behind differentiation is the idea behind the rate of change. So a rate of change is going to be really important here. So we're just talking about change. And we abbreviate rate of change ROC. So when you see that abbreviation, you'll know what it means. We also talk about limits, and we'll get into that conversation in this, probably in the next section, a little bit in this one. And that idea turns into the idea of tangent lines a lot. So these are our big ideas that we talk about in differential calculus. Part 2 of the class, the second focus of the class, is integral calculus. Now, integral calculus is used for a lot of things, but one of our primary focuses will be computing areas under a curve. Now, we know how to compute area. Let's say if we have a rectangle or a triangle or a square, but what if we don't have a nice geometric shape for which somebody's already determined the area formula for us? How would we find that area? So this would come into play like if we were looking like at the drainage field of a water feature or a river or a creek. We could also talk about this in terms of looking at a piece of property that had a particular distribution of we'll say weeds or something like that on it, and we wanted to figure out what is the area covered by that. These are all those types of ideas that can get into those areas. Now, a lot of times we just estimate or ballpark it, but if we want to be precise, then we can use ideas of integral calculus. So to get started, let's talk about limits, rates of change, and remember that's ROC, and tangent lines. All three of these ideas are very closely related. So let's go ahead and start with rates of change. Now, the idea of a rate of change builds on everything else. So once we have a rate of change, we can kind of start building into tangent lines and limits as well. So a rate of change, just kind of as a quick overview, is the relationship between two changing quantities. Now, this might not sound like it's anything familiar that you've worked with before, but we work with this relationship between two changing quantities all the time without probably being aware of it. And the one that we usually bring up as a good example of this is velocity. Now, when we talk about velocity, that is the rate of change of position with respect to time, and WRT means with respect to time. So our two changing quantities are position and time. So again, this is a really important idea. Now, another rate of change that might be interesting to look at might be something like infection rates. We might look at a population and we might talk about the percent of the population infected over some sort of time, so maybe a week or a month. So we could talk about whether the infection rate is increasing or decreasing. This could be a spread of a disease, something like maybe the Zika virus or Ebola. It could even be something like the flu that we run into every winter and how it's spreading. This could also have to do with interest rates. Now, with interest rates, basically we're looking at the change in money in your account with respect to time. So if we are earning interest, meaning we have money invested, this amount will go up. The change in the money in my account will go up with respect to time. If we owe money on a credit card, the value that I owe will go up as well. So if you want to think about it, it's a negative amount that I have to end up paying back eventually with respect to time. So these are just a few examples of some rates of change. Now, a couple things about rates of change that we need to be aware of. If x and y are related, if my two variables are related, so in this particular case, position and time, let's just call them a generic x and y. If x and y, my two variables, are related, the rate of change tells how much the y value changes that's my vertical value or my dependent value in response to a unit change in x. Now this idea about a unit change in x isn't always going to be realistic because things don't always change in nice little units. And this only applies when the rate of change is constant. Now, it's not very often that the rate of change is going to be absolutely constant. So for instance, if we look at this example over here about our change in position over our change in time, our change in position is not always going to be constant. When we're driving down the interstate or driving down the highway, I'm speeding up and slowing down. I'm never at a constant change in position over time. Infection rates, we know that with infection rates, the more people that get infected, the higher or the faster the virus will spread, and so that rate would change, not constant, but would be probably exponential to some point. So this only takes into account the idea that that rate of change is constant. Now let's go ahead and keep going with this idea of that constant rate of change, and let's see how far we can get with it. Assuming constant velocity from the example that we just talked about above, and this would mean if you were leaving for, let's say, a hike around Devil's Tower or something like that, once you left Spearfish, you'd always drive at the same speed. And that's not realistic at all, but let's go ahead and follow through with our example to see what happens. Now, if we assume that that's true, that we work or that we move at this constant velocity, we have a nice little formula. We've been working with this formula for a long time. We've seen it a lot. So distance equals rate times time. D equals RT is another way that we are familiar with this. Now this formula is only true if velocity of changing, or if the velocity is constant. So our example here, if we were driving, let's say velocity and rate are synonymous here. If we were driving 50 miles an hour for 4 hours, that would be 200 miles. But what if we were driving 30 miles for a while, 30 miles per hour for a while, and then 100 miles per hour for a while? This formula doesn't quite do the trick. So I need some sort of another way to work with this. So again, let's go ahead and look at that simple case. 4 hours at 75 miles per hour. I'd have distance equals 75 times 4, which would be 300 miles. Okay, so that's again assuming that the velocity is constant. Now, what do we do? So this is the big puzzle right here. What do we do if the velocity is increasing and decreasing? I can't use this formula anymore. I can use the idea, but I can't use the exact formula, and the answer is we use calculus. So calculus comes to the rescue here. So again, when we talk about calculus, especially differential calculus, we're really talking about change and studying how things change. Now this is going to, interestingly enough, take us into a conversation about tangent lines. Now it kind of seems like a non sequitur to talk about all of a sudden velocity and all of this, and then all of a sudden jump to tangent lines, but there really is a connection there. A tangent line is a line that skims the curve. Now we might have a more basic definition of tangent line kind of based on what we have learned before. Usually the idea of a tangent line comes up when we are talking about circles. So let's go ahead and look at a couple different shapes here. This is always my favorite curve to work with. So if we talk about these shapes, a tangent line, we're used to saying something like, it touches the graph once. But really we want to talk about how it skims the curve, because this graph, or this line, is touching the graph once, but it's not tangent. We have to talk about how it skims the curve. So it skims right here and it touches in one place. So this line is tangent. Now when we get over to talking about these types of graphs, it's not as obvious sometimes. So let's go ahead and look at this line. It definitely does not skim the curve, it just chops it. In fact, it hits it twice. This is called a secant line. And in fact, this over here, if I could touch this twice as well, would be a secant line. If I want to talk about a tangent line at this point, I wouldn't talk about this line because it doesn't skim the curve. It crosses once, but it doesn't skim. I would talk about this line that skims that curve. Now we have to be a little bit careful about how we draw some of these lines sometimes. So again, this line is not tangent. Even though it's touching in one spot, we need it to skim that curve. Now let's go ahead and look at a tangent line here. And this is definitely a tangent line, but interestingly enough, if I extend this, it would eventually cross over here, and you'd say, well, wait a minute, it's actually a secant line, but it's tangent at this location. And so that's really what we need to keep in mind, is how it's tangent at that location. If we extend it, you're right, it is a secant line, but we're just talking about at this local area. Let's go ahead and draw one more here, and if you look at this one, we can definitely see that locally this is a secant line. So it's a good idea to know what each types of these are, so we get an idea of what we're talking about. Now, you might think we jumped from one thing to the other. We were talking about rates of change, we were talking about velocity, and now we're jumping into tangent lines. Well, interestingly enough, the idea of the velocity, this rate of change, directly relates to the idea of a tangent line. If we talk about a line, we know to find the equation of a line, we need to know the slope. The slope is the change in y over the change in x. That relates directly back to rates of change, and so that's the connection between all of these ideas. So let's keep that idea of a tangent line in mind as we continue to work with velocity. Now sometimes you'll be given an equation to work with, and they'll be talking about the position of that particular function. Sometimes you'll be given an equation and it'll be talking about something to do with a bank account. So you always have to look at the context of the problem. But let's look a little bit more at velocity now that we get this little bit of a connection between velocity, rates of change, and tangent lines. We have a couple different velocities that we can look at. The first one is instantaneous velocity. Now we like to look at instantaneous velocity because it's really realistic. Now, instantaneous velocity, it's the speed and direction of an object at a particular moment in time. Now remember what velocity was. It was the change. So we have to be thinking about change a little bit here. Now, in order to find instantaneous velocity, there's really no easy way to do this without calculus. There's no easy definition without calculus. Now the reason being is we'll run into this formula in a little bit here, is I don't have a change. If I wanted to look at instantaneous velocity, that's a single point. And in order to determine actual velocity, I have to know how far I've traveled, so I need an initial beginning point and an ending starting point. And instantaneous velocity doesn't really allow for that. Now the other type of velocity that I can talk about is average velocity. And we're going to build on this idea of average velocity to come up with instantaneous velocity. So average velocity, I use that formula, d equals rt, rate times time. Now if I solve for r, solve for rate, I get r equal, and I would divide both sides through by t, distance over time. Okay, that's interesting. So rate equals distance over time. So if I drove 400 miles in 2 hours, 400 divided by 2 would be 200 miles per hour would be my rate or my velocity. Now, in order to find my distance, I would need to know my change in position over my change in time. A couple things I want you to look at here. This triangle, we'll make a note off to the side. This is an important notation. This triangle is the Greek letter delta, and it means change. So we'll see that show up quite a bit. And it can be the change in position, change in time, change in y, change in x. It can be used a lot. It's used in science as well. So this change in position is important over that change in time. Now we can start developing a formula using that idea of position change and position time, and then develop a formula for average velocity. Okay, so let's go ahead and suppose a few things. S naught, this is a subscript of 0, and it's pronounced not S sub 0 but S naught. This is called my initial position. So if I was driving from Spearfish to Sioux Falls, my initial position would be Spearfish. S1 is my position at time 1. T naught would be my initial time. And then T1 would be my time at time 1. So for the example that we're looking at, let's go ahead and put some values in here. Let's say our initial position is 0. And let's say we're going 400 miles. Let's go to Sioux Falls from Spearfish. That's about 400 miles. Our time that we leave, we're going to be called time 0. And the time that we arrive, let's go ahead and say is 5 hours. I'll put hours in here in miles so we have our correct units. So I could come up with my average velocity for my trip. Now from our formula up above, average velocity is the change in distance, or my change in position. We see up here position is equal to S, and this is really common as well to use S for position, over my change in time. So change in position over change in time. Well, let's go ahead and look at our trip here. I'm not a great artist, but let's go ahead and say that this is the state of South Dakota. And let's say this is Spearfish, and we'll say this is Sioux Falls. And when we talk about our initial position, this would be S naught, and our final position would be S1 would be Sioux Falls. T naught is our initial time. T1 would be our time when we arrived in Sioux Falls at time 1, we'll say. Let's say we drive clear across, we don't have to stop for gas or anything. So our average change in position, if I'm going to start, let's say, at exit 0, and let's say I get off the interstate at exit 400, just for an easy example. I think it's exit 396 or something, but we'll say exit 400. In order to figure out how far I traveled, I would take 400 minus 0. For my time, let's say I left at, we'll say 1 p.m. And if I traveled for 5 hours, and we won't worry about the time change here, we'll say that that's 6 p.m. So if I wanted to figure out how long I traveled, I would take 6 hours, 6 p.m. minus 1 p.m. Now if you had to worry about going from a.m. to p.m. and whatnot, there's going to be a little bit more work here, but you get the idea. So I would have 400 miles over 5 hours, and then if I were to divide that out, you could see that I would want to get a unit here. I want how far I'm traveling, or how far I get to travel in 1 hour is usually what we're interested in. So this is equal to then 400 divided by 5 is 80 miles. And then here's that nice unit that we like, over 1 hour. Now usually we write this 80 mph or 80 miles per hour. But we can see here then that this is a nice little average velocity, even though as I was jumping on the interstate I was going slower than when I was cruising on the interstate. This gave me my average velocity over the length of my trip. So this idea of average velocity is important, but however has several shortcomings. So however, at any given moment the car may be going faster or slower. And that's the part we have to contend with. And how do we contend with that? We are going to give the idea of some calculus, because what we have over here is only an average. And we want to be able to figure out what's going on in any moment along the trip. So we cannot find instantaneous velocity with this formula, and let's figure out why. Now to find velocity, we needed to have a change in distance and a change in time. So for instantaneous velocity, t0 equals t1. And the difference between t1 minus t0 is 0. So instantaneous velocity means there's been no change in time. So when we use this formula that we used right up here, the change in distance over the change in time, the change in distance over the change in time would be some number, and really that has kind of the same problem that we just talked about. Instantaneously there is no change in distance, but the big problem is the denominator. The change in time is equal to 0, and this is an undefined fraction, so I can't find instantaneous velocity because there's no change in time, and my denominator would equal 0. So we have to figure out some way that we can deal with this. So we should be able to get a good estimate of instantaneous velocity by just looking at a really tiny change in time. Now the question is, how tiny of a change do we need? Now these are examples when we're talking about things. I always think about water flow. When we're talking about water flow during like a high rain season, or we're trying to talk about whether the water flow through an irrigation ditch is changing, increasing, decreasing, we usually like to know the flow rate. And so we usually rely on equipment that's already been produced that calculates a lot of this for us. But this kind of gives you an idea of the background of how this works. So again, a very small time interval to compute the average velocity. So what this formula looks like then is the same old formula that we've already worked with. We have average velocity still is the change in position over the change in time, but now we have this over a very small time interval. So maybe for like 1 second, or even less than that, maybe half a second. So this is the idea that we're going to develop into coming up with that correct formula. Well, to get started with this, we need to talk a little bit about history. So we need to talk a little bit about Galileo. Now Galileo is known for a lot of things, but the thing that we're going to focus on is a nice little equation he came up with. But what he talked about is if an object was released, and if we talk about it being released, that means we're usually on top of something and dropping it. So if an object is released at time 0, so that's our initial time, so that would be t0 equals 0, and we're releasing it from a state of rest. And that basically means that there is no velocity. So we're not throwing it and then checking its time after a half a second end. Then what we know is the distance traveled after t seconds, and some people spell traveled with 2 L's, some with 1, so I'm going to go with the 1 convention. Is given by this nice little formula, and this will look familiar to you if you've had any science classes in physics. S of t equals 16t squared. Now this, of course, is assuming that there's no drag. This is kind of like the perfect situation in a vacuum that we have this occurring. So if I know the amount of time, I can plug in t, plug it into this equation, and then I can get the distance traveled after so many seconds. Now if I were to graph this, S sub t equals 16t squared, this is just a parabola that opens up. It's very wide and it's centered at the origin. So this is the total time traveled. Now if we look at this parabola, if we start at t equals 0, this half of the parabola doesn't really make sense, because this would be negative time over here, because my t values would be negative. And then the total distance traveled, now this is assuming it'll continue traveling forever without any interference. Of course, that's not always realistic. So, of course, this is only defined over some values of t that would work. But we're going to use this idea sometimes while we're working to come up with this idea of instantaneous velocity. Now, this is just one of many formulas and functions that we can use. Now, a lot of times in your homework and on exams and quizzes, the formula is given to you. And then once the formula is given to you, they might give you some other s sub t, or they might give you some f of x or something in order to work with the same kind of a setup. So it depends on the context of the problem. Now what we're going to work with is a formula that involves investing money. So let's go ahead and look at that investment. We know if we deposit money, it grows. It doesn't grow very fast right now because the interest rates are so low. But for the example that we're going to look at, let's see what happens when we invest some money. So with an initial deposit of $100, so that means we took to the bank $100 and we deposited the $100 in account. The balance in that account, if I didn't add any more money, it was just earning interest. The balance in the bank account after t years is given by the function. So that could be a half a year, it could be 5 years. F of t equals 100, that takes into account my initial investment, 1.08 to the t. Okay, so under these circumstances, this is the equation that models that behavior. Well, I want to know the answer to a couple of questions here. What are the units of the rate of change of f of t? Well, this is going to be pretty straightforward. The change that we're looking for is the amount of money in the bank, so it's going to be money over time. So dollars per year, because we're keeping track of years because time is in years. So that would be the first thing that we could answer. Second thing, let's go ahead and find the average rate of change. And again, ROC is rate of change. over a couple different intervals. So the first interval I want to look at, let's see if I can find. So the first interval, let's say, is 0 to 0.5. Now this is not an ordered pair. This is our time. So this is time equals 0 to time equal 0.5. And the other interval I want to look at is between 0 and 1. So these are pretty small intervals. So I want to find my average rate of change over that interval. So let's go ahead and look at our first example. So our average rate of change, let's do 0 to 0.5. And again, these are my values for t. This is going to be equal to my function at 0.5 minus my function at 0 all over 0.5 minus 0. Now this has to do with same thing, driving to Sioux Falls. This was Sioux Falls minus Spearfish for my distance over time Sioux Falls minus time Spearfish. So this is the same type of thing. So now I need to take this 0.5 and plug it into this function. And if I do that, it would look like this. It would look like 100, 1.08 to the 0.5 minus 100, 1.08 to the 0. So these are the values that you'd plug into your calculator, and of course 0.5 minus 0 is just 0.5. So if I simplify this, I end up with 103.923 minus 100, have to do a little bit of rounding there, over 0.5. So this one is equal to $7.8461 per year. Okay, so if I look at the time interval, my average rate of change between the time I invested the money and a half a year later, this is about what I would see for my average change in my account. So this is looking at my increase. So this would be $107.85 or something like that. Now let's go ahead and look at a wider interval. Could have looked at the narrower first. It might have been more interesting to look at the narrower first, but we'll end up with the same information. So I'm going to look at the average rate of change over the interval 0 to 1. So this is going to be f of 1 minus f of 0 all over 1 minus 0. 100, 1.08 to the first, minus 100, 1.08 to the 0, and of course 1 minus 0 is 1. So if I plug these values in, I end up with 108 minus 100 all over 1. I end up with $8 over 1 year, if we want to think about our units, $8 per year. So interest rates are usually a yearly rate, sometimes they're instantaneous, but maybe kind of what I'm seeing here, given the information that I have, maybe this is telling me something about the actual interest rate that was being earned in this account. So maybe $8 per year on $100 is implying an interest rate of 8%. And that actually comes into play with my formula. So remember, our formula was f of t equals 100 was my initial investment, 1.08 to the t. Looks like to me this is my interest rate, that 0.08 part. That's telling you how much the account is growing. So there's some things that we can infer from these. Now for my top one, the 0 to the 0.5, I was getting close to $8, but not quite. And you have to think about what's happening between 0 and 0.5. The money has not been invested for a full year yet, so I would not have earned a full year of interest. So that's why it's approaching or getting close to that $8, but it hasn't reached it yet. So those are a couple of different things that we can find with this particular problem. Let's go ahead and look at the same problem, and this time let's go ahead and try and come up with an instantaneous rate of change at a half a year. Because remember, we came up with like $7.84 or something like that. We want to find out instantaneously what's happening at half a year. So let's estimate the instantaneous rate of change. at a half a year. Time is 0.5 years. And we're going to do this by computing the average rate of change to the left and to the right of t equal 0.05. Sorry, 0.5, not 0.05. In smaller and smaller intervals. Now, one thing that we want to keep in mind here is I don't always have to check it from the right and from the left. A lot of times we'll just use one direction, but a lot of times we do check both directions, so that's why we're going to put this up here. Now, we kind of already have a formula that we've set up, or a process that we've set up above, so we're going to want to stick with that same thing. So, a couple different intervals. Let's look at the interval to the left. So numbers slightly smaller. So let's look at 0.49 to 0.5. And another interval would be even closer, like 0.499 to 0.5. And we could maybe, we'll just call this one 0.5. This is what we're trying to figure out. So another interval would be something like 0.5 to 0.501. And we'll look at 0.5 to 0.51. So let's look at really what we have here. This interval is very, very small. It's 0.01. This one is 0.001. So you can see that the time interval here is not very many. This is 0.01 years. This is 0.001 years. And we're trying to get closer and closer to this idea of 0.5. Now this is slightly less than that. And what we want to do here then is the change in f over the change in t. And then we'll look at the ratio of those two, and that will give me my rate of change. So I think what we can do to get started with this is we can just start plugging in values into our function. Now remember what our function was. It's given right up here. So if you need to refer back to it, this is what we're plugging in for f, the change, and then we go from there. Now I'll plug in the first one for you, and then you can fill in the rest of the table. So the average rate of change, let's go ahead and do the interval 0.49 to 0.5. And this is exactly the same as we did above. This is going to be equal to the change in f over the change in time. F was the total amount in the account after t years. This is going to be f of 0.5 minus f of 0.49 all over 0.5 minus 0.49. So to find my solution here, I would plug that into my original function. So this would equal 100, 1.08 to the 0.5 minus 100, 1.08 to the 0.49. And this is all over the difference. 0.5 minus 0.49 is 0.01. So when I simplify this, I end up with 0.079949 all over 0.01. And I recommend you pause the video and double check my math and make sure you understand where all the numbers come from. When we divide this out, I get 7.9949 per year. So that's really close to $8 a year. So that's getting me a really close idea to my actual interest rate. So the way that this looks up here then, this numerator 0.079949, so again 0.079949 over 0.01 was my difference, and then my actual answer was 7.9949 was my rate of change over that interval. Now if you go through and continually do this with each interval, and again I recommend that you try this, these are the numbers that I calculated for each of these intervals. Now we're going to see something really interesting start to occur. When we're looking at these intervals. Now on the right hand side, they're a little higher. And then this one we're moving out further. The interval is wider, so I won't expect as inaccurate of an answer. Okay, so what we're trying to do is we're trying to figure out what's happening as we approach from the left and what's happening as we approach from the right. This is going to be our instantaneous rate of change. But again, I can't calculate it because instantaneously there's no change in time. But if I look at the patterns over very, very small increments, I can see, you know what? This is approaching $8. I'm pretty confident about that. We're getting closer and closer to 8 from the right, and we're getting closer and closer to 8 from the left. This is the idea of a limit. So the idea of a limit that we talked about above makes sense here. So the idea that we've started to develop then about average rates of change and instantaneous rates of change, let's see if we can summarize that. So we have the average rate of change. This is a big idea. So the average rate of change converges, and a lot of times we use an arrow to show this, and this means approaches in this context, the instantaneous rate of change, if we can use small enough intervals. So this is our huge idea of the day. So average rate of change converges to the instantaneous rate of change. So the average velocity converges to the instantaneous velocity. So again, very, very important idea that we've developed here. Now let's go ahead and take this idea a little bit further and let's look at this graphically. Now when we talk about this graphically, we're not going to put a particular function to this yet. We're just going to talk about in general. So let's look at an instantaneous rate of change and then how it relates back to velocity as well. So again, instantaneous rate of change gets us back to that idea of velocity. So let's go ahead and look at this graphically. Now in order to show this, we need a pretty steep curve. So let's go ahead and start with the curve that has quite a bit of change in it. And again, we don't really care what this curve is. We just care that on my x-axis, or my horizontal axis, would be time, and my vertical axis would be position, let's say. So on this curve, let's go ahead and look at two things. Let's look at t0, and then let's look over here at t1. So again, this relates to traveling from Spearfish to Sioux Falls. Now the curve doesn't quite look right, but we won't try and justify that here. We're just using this curve as an example to show something about these 2 points. So on my horizontal axis, this is called s of t0, and on my vertical axis, s of t0 on my vertical and s of t1 on my vertical. Now remember, this is position on my horizontal or on my vertical, and time is on my horizontal. Now if I look at this graph, I could connect these 2 points. And you can see pretty clearly that this is a secant line. This is not a tangent line. This is a secant line. So when I talk about the slope of this secant line, the slope would be the change in y, the change in the horizontal over the change in x, which is the change in the vertical over the change in the horizontal. So this is our typical formula that we work with. Okay, so when we talk about our change in y over the change in x, I'm talking about the change in position over the change in time. So this formula we know from up above is average velocity. So this is just a quick show of what's happening here. Now what we have, this particular curve that we're graphing, is the curve s sub t. And so this is the secant line to s sub t. Now when we're looking at this particular secant line, if I can make this time interval smaller, meaning I'm going to move t1 down here in this direction, what's going to happen to this secant line? So T, our new T1 would say let's move here. And we can see this line gets closer and closer to being a tangent line. So as it gets closer and closer to being a tangent line, it gets closer and closer to that idea. Move it a little bit closer here, and pretty soon it'll be hard to see because we can't show a secant line for this example because they almost run right over the top of each other. You can see that this other line is closer, and sorry, I'm not sure why it keeps skipping like that. Gets closer and closer to turning into a tangent line where it would skim the curve. Now ideally what we'd like is the perfect line that skims this curve, but we can't find the slope of that because I need 2 points to find slope. I can't find the point or the slope of a particular line with just 1 point. So this is an example of how we can interpret velocity as slope. And that idea is pretty important. We'll use this a lot. Let's go ahead and look at the same type of an example, but let's this time use a particular curve. Instead of just using a generic curve, let's use a particular curve. Let's go ahead and pull back to Galileo's curve that he showed us. So let's go ahead and use the example of S sub t equals 16t squared. Now we talked about how the fact that t didn't really make sense in the negative region, so we're only going to focus on the first quadrant where t is 0 or positive. So we're only going to be looking at half of that parabola that opens up. So as we're working with this, on my horizontal axis, this is time. So this is time in seconds. And then this is my distance traveled. My vertical axis is distance traveled. So I want to look at that gap between 0.5 and 0.6. See if I can get this to stay now. So if I look at here's 0, and I know if I plug in 0, I get 0 back out. So here's where my curve starts. And then of course I can plug in all sorts of different values. So if we want to figure out what the instantaneous velocity is at t equal 0.5 here, I could think about this as also looking at the slope. So let's go ahead and look at, estimate the slope of the tangent line. And we want to do this at t equal 0.5. Okay, so if I want to estimate the slope of the tangent line, we could go ahead and start right here, let's say at 0.6. Now 0.5 we'll say is somewhere down here. So I have 2 points that I'm looking at. If I move up here, I can see I have a point right here, and if I move here I have my other point. This is the point S of 0.5. This is the point S of 0.6. Okay, now let's go ahead and graph that. I want a little bit thinner of a line here because our lines will end up overlapping quite a bit. We'll go through both points. So this is the secant line, and the slope of this secant line will end up being 17.6, and I'll show you how to calculate that below. Let's go ahead and do this for another point. Let's do 0.55. Now the reason I'm choosing a point that's closer is I'm trying to close this gap. I'm trying to get closer and closer to this value. Let's choose one that'll show up nice. Here's that 0.55. So this point over here is S of 0.55. That's the ordered pair. It's going to go through these 2 points. Let's see if I can get it to right out there. And you can see how close. It almost lies right on top of the line. Let's go ahead and extend this out. The slope of this line is 16.8. Let's go ahead and do one more. These are going to get harder and harder to see because they're so close. Let's do 0.51. So if I put 0.51 on this axis, this would be S of 0.51. You can see the difference between these 2 points. You almost can't just, it's almost the same line almost, it's so close. So we can see here that something's going on with the slopes. And what we can show, and I'll show you how to calculate those secant lines as well, the slopes of the secant line are getting closer and closer and closer to the slope of the tangent line. So the slope of the secant line approaches, remember this arrow in terms of the context of this type of problem, approaches the slope of the tangent line at 1/2. So at t equal 1/2, 0.5. So what we can do though is trying to start estimate that particular tangent line. Now we don't have any calculus background yet officially. Some of you might have some background from a previous class, but from calculus we know that the actual tangent line has a slope of 16. This is very close. We did a really good job estimating it. So we can close that interval. We can see how easy it is to estimate that slope. So if we would have had a small interval, 0.501, closing that gap even more, we can see that we get very, very close to that. Now how did we calculate the secant line slope? Okay, we'll do one of these for you. So let's go ahead and do the interval. Let's do 0.5 to 0.6. So that was our first one. That was our red line. So what we do to calculate that, that's our change in position over my change in time. So my change in position would be taking my position function and evaluating at 0.6 minus 0.5 all over the difference in time. So this would be plugging these into my original function, which was 16t squared. 0.6 minus 0.5 is 0.1. And what I get here is 17.6. And that's this value right up here. So that's how I calculate the slope. And you can go through and do that with each pair to verify that these are the correct slopes of those secant lines. So slopes of the secant lines approach the slope of the tangent line as those intervals get closer and closer together. So we've covered quite a few ideas here, but the big important takeaway is that idea of a limit is starting to be created. A limit's starting to be created because I'm getting closer and closer to one point on a curve, but I can't actually ever reach that instantaneous velocity. I can just estimate it. So again, big idea, average velocity approaches instantaneous velocity if I can make that interval small enough. So this should be enough for you to get going on your homework. I'm going to add one more problem on the end here. If you want to watch this, you can. If you don't want to watch it, that's fine too. Of course, that's true with any of the videos. But if you're having a tough time or struggling with any of the homework, you might want to come back and have a look at this. It might help you out. Okay, so let's go ahead and look at an example in depth. Now for this example, we're going to add a few other things to it as well. But basically, we're looking at the problem, and this is my position function. S of t equals negative 8t squared plus 80t. What I want to do is complete this table with the appropriate average velocities. Okay, and then I'm going to make some sort of conjecture about what's going on at the instantaneous velocity at t equal 1. Now at t equal 1, I'm only checking this from one direction. If you notice, this one's a little bit different than the example we did above where we checked from two directions. So if we check from just one direction, I'm trying to figure out that instantaneous velocity is basically right here. This is my value at 1. And so I'm starting from a long gap, a big interval, and I'm trying to get closer and closer and closer to that instantaneous velocity as these intervals get narrower and narrower and narrower. So I'm going to go ahead and start this, and then you can fill in some of the values in the table as well. So to get started, we definitely have this function negative 8t squared plus 80t. So to start with, let's look at our first interval, our widest interval from 1 to 7. So if I want to look at the average rate of change or the average velocity, let's go ahead and look at that interval from 1 to 7. Now this is not a very tight interval, meaning I'm not really getting all that close to 1. This is quite a gap here. So my average velocity would be the change in position over the change in time. So the change in position would be s of 7 minus s of 1 all over 7 minus 1. So I'm plugging this back up here. So I'm taking 7 and I'm plugging it in here. And when I plug that in, I get 168 minus 72 all over 7 minus 1 is 6. Now if you want to grab your calculator and plug this in, there's kind of a nice little quick way that we can do this. So your calculator hopefully is similar. What I'm going to do is I'm going to graph this function, and I'm going to graph negative 8t squared, and I'll use x instead of t just for simplicity, plus 80x. Now I might have to adjust my screen a little bit. This is a parabola that opens down, and basically I'm looking at this interval from 1 to 7. So I'm looking at this line right here. Well, if I want to look at my values, an easy way to do that is to go to second table, and of course you can just plug them into your calculator as well. And I can scroll down, and here's s of 7. It's 168. So that's where my value of 168 comes from. Now this is really going to be easy for me to use for the interval from 1 to 6, 1 to 5, 1 to 4, etc. But I'm not checking all those intervals, but that's a quick way that you can do these on your calculator. Okay, when I divide out 168 minus 72 all over 6, I get 16. Now this is also the slope of the tangent line between 1 and 7, and I'll have a graph that I'll show you here in a little bit. Now as you keep working with these intervals, the average velocity from 1 to 6, remember I can pull some of these values off my table. We'll do a couple more. I want to look at the average velocity on my last interval, just because that's going to be the most telling, because it's the tightest gap or the tightest interval. So again, change in position over change in time. S of 1.001 minus S of 1, 1.001 minus 1. So when I work through this and divide it out, I get 63.992. And remember, this is slope. Okay, so this also relates back to the slope of the tangent line. So this is 63.992. Now I'm just going to go ahead and fill in the rest of these. You can calculate these by hand using the same exact examples. You can use your calculator for these, obviously. 24. So you can see that this is approaching something. The slope is 16. It's getting larger, 24, 32, 60. It looks like to me that this is approaching 64. So I think 64 is my instantaneous velocity. At t equal 1. That's just my thought, because I can see that this is getting closer and closer. Now over here, I have no clue what it was getting close to because it was so far out, but it is getting very, very close to 64 here for my instantaneous velocity at t equal 1. So that's my conjecture about that instantaneous velocity. Now there's a couple other things that I want to talk about here. Everything that we've done so far has been plugging numbers directly in. Sometimes, however, it's easier to write a function or represent a function here. So for the exact same problem, I would like you to find the average velocity. This is where our algebra background will come into play. And the interval I want to look at is 1 to 1 plus h. Now what's happening here is this h just means the change, the increase. So the increase could have been 6 units to get me to 7. It could have been 0.01 units to get me to 1.01. So the way this plays out then is the change in position over the change in time. Change in position would be s of 1 plus h minus s of 1 all over 1 plus h minus 1. Okay, so when I plug this in, this ends up looking like negative 8 1 plus h quantity squared. And then from here I can also plug in the next value. And then don't forget our original function also has a, scroll back up here, plus 80t. And in place of that t I'll have the 1 plus h. I think we're going to run out of room here. So let's go ahead and move this down here. And then minus s of 1. And s of 1 we know from up above was equal to 72. So this is s of 1 plus h to here. And then here, the minus sign comes from my formula. This piece is s of 1. So again, we're just plugging in. This is from algebra. Now the difference in the bottom, 1 plus h minus 1, the ones cancel each other out. One's positive, one negative. I'm left with h. Now after you do some algebra here, and when we're doing our algebra, 1 plus h quantity squared is h squared plus 2h plus 1 plus 80 plus 80h minus 72 all over h. And then we'll distribute through the negative 8. Negative 8h squared minus 16h minus 8. And then what we can do here is combine some like terms. And what we're going to end up with is a formula that's pretty easy to work with, and I don't have to plug all the numbers back in, but you have to realize exactly what's going on with it. So I have a negative 8h squared, okay, and then I have an 80h minus 16h is going to give me a plus 64h. And then 80 minus 8 is 72 minus 2 is 0 all over h. I can factor an h out of the top. And then you can see that these h's cancel. And so my average velocity then for any interval between 1 and 1 plus h, where h is a value that could be 0.1, 0.01, etc., is equal to negative 8h plus 64. Okay, so this is a nice little formula to come up with, because if I wanted to check to see what was going on in the interval from 1 to 7, this is going to be the interval from 1 to 1 plus 6. So in this case, h equals 6. So I would plug it into my formula here, negative 8 times 6 plus 64. So negative 48 plus 64. Looks like it would leave me with 16. Now if I look back up at my table, if I can get back up there, my slope was 16. So this is a lot easier than going through this whole process, just working with that 1 plus h, that variable piece. But the point is, h is not equal to 7. H is equal to the change between these two values. It was equal to 6. And I can just plug it in there. And I can do that with any of those intervals as long as the interval starts at 1 and goes to a value 1 plus something. Now I have a nice little graph I created here. This graph is from Desmos. So I'll pop it in so we can have a look at it. I really like to look at things graphically because it helps me visualize exactly what's actually going on. So this graph that we're going to pop in here is a graph of the problem we just worked on. So this is a graph of f of t, I think we called it. No, we called it s of t, sorry. S of t equals negative 8t squared plus 80t. So that's this red graph right here. Now what all of these are these are secant lines. So you can see if you work down here, this is 7. So this point right here was the point 7. Okay, and if I plug 7 in, I got 168 back out. Now when I found the average rate of change of this secant line, this slope was equal to 16. Then I went through and I did that, and this is coming directly from the table that we did up above. The slope of my next one was 24. And again, this was that ordered pair that went through 1, 6. So this was that ordered pair 6, 192. And again, these values came off the table. This next slope was equal to, let me say, 16, 24, 32. And then it gets kind of hard to tell which is which here. But as these get very, very close, this slope ends up being 60. And then there's about 3 lines that overlap here. So these slopes are approaching 64. They're not exactly 64. These are like 63.92, 63.992. But again, we have here that the secant slope approaches the tangent slope over very small intervals. And that tangent slope is important because it gives us the instantaneous rate of change. And that idea of change is really important here. So when you're working through your problems, you might see some trig functions, but the same thing works as well. Make sure that if you have questions, you take a screenshot, let me know. You can also work with Desmos and your calculator to help you come up with these values. On a test, you probably wouldn't be creating one of these large tables. That would kind of be more of a handwritten homework type of problem. But you will be expected to be able to interpret them and to be able to explain the idea about secant slope approaching tangent slope and the idea of instantaneous velocity. Good luck, and please let me know if you have questions.